Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So welcome to the video 5 of our DP series. Uh, Today we will learn a variation of knapsack and we will see that how this knapsack problem that we have already talked about earlier, that knapsack problem, that 0 1 knapsack problem, that can also be extended to some 3D DP variation, right? So far I have done 1D and 2D DP completely, but how this same approach, how this same idea, same intuition can be extended also to 3D DP variation, and the solution will be more or less exactly the same idea and intuition we will use, and the approach will also be the same. You can directly use the first, you can go for the recursive approach, okay, and then you can write the memoization, as I've already explained you in the previous videos, how to convert from recursion to memoization to tabulation, and the exact same steps you follow for 1DDP, you have followed for 1DDP also. The exact same steps you also followed for the 0 1 knapsack problem, and some of the variations like coin change problem, as I've already explained you in my earlier video, okay. And so just go and check my playlist. This playlist might be of help to you. I am teaching DP from very basics to advanced, and today we will see a 3D DP variation of the same knapsack approach. We will use the same take not take concept here also, and that will be really cool when you will understand that, when you will get to know that the thing which you have learned can also be used to solve 3D DP problems, and it will be very much helpful, and it will give you a lot of confidence, okay. And if you will feel it really easy, okay, so approach and all, it will feel really easy, it should feel really easy, okay. So we will look at the problem statement. So if you have not tried this problem earlier, just go to Leetcode 474 and try this problem. We will understand the concept and then code that out also. So let's check. What is the question? Let's try to discuss the question first. We have the question that you are given a string array, okay, array of strings, and this array of strings contains only binary numbers, okay, in the form of strings. So let's say this is the first string, the second string may be 1 1 0 0 0 0 1, maybe anything, okay. This one may be a single one also, and then again it may be let's say a long string also, okay. There are some constraints present, there are definitely some constraints present. Okay, now question is that you need to select the largest possible subset from this list, okay. Select the largest possible subset, and what you can do, uh, such that it has at most m zeros and n ones, and n ones, okay. So what do you mean by this? If you try to see, you can keep picking or not picking every element, and you need to select the largest possible element, so you need to pick as many as elements as possible. So what can you deduce from here? You can easily deduce that the thing which you need to do is pick as many elements as possible, okay, as possible, and definitely that element should have m zeros and n ones. So what happened in knapsack, if you remember, the robber which we were talking about had a sack, okay. They had a sack in which they wanted to loot some elements. They will put some elements of, let's say, it will have some varying values of those elements, and it will have a maximum weight capacity. It cannot let's say go more than w weight, okay. Similarly, here you can, think that you have two sacks. In one sack, you can put zeros only, okay. In the other sack, you can put ones only. And the weight of this zero sack is nothing but m. The weight of this one sack is nothing but n, okay. So the problem reduces to exactly the same thing. What are the states of the TP in the knapsack problem? It was the index and the current weight. Okay, it was the index and the current weight was the states of the DP. In here, it will be index, the current value of M and the current value of N. This will be the states of the DP. And if you try to think, you will use the same take not take concept. You will go to every element and you will check whether to take this or not take this. Okay, you will just ask yourself whether to take this or not take this, and accordingly write a recursive function. And if you take this, then definitely you will have an increment of largest, since it is called the largest possible subset, you will have a score increment of 1 if you take it. And but your this containers of M and N will fill with, let's say it has 3 ones and 3 zeros. Okay, so you need to fill this with 3 ones and 3 zeros, and you need to keep filling this, adding the values to the current M and current N. Okay, so that's all you need to do. Let's try to see the solution. We will see the approach, complete approach, which goes from recursive solution to the memoized concept. Okay, to the memoized concept, and also to the iterative DP or the tabulated DP, or it is also known as the bottom up DP. Okay, uh, the bottom up tabulation, whatever you call it. Okay, so let's look at the problem. Okay, let's look at the problem once. In Leetcode, we will go to Leetcode now and just see the question. So you see, you have this ones and zeros. You are given an array of binary strings, 2 integers M and N. Return the size of the largest subset of strings such that there are at most 0 M's and M zeros and N ones in the subset. A set A is definition of subset is written here. Okay, and you are given a strings in this manner. You are given M and N also. So the largest subset is the most with the 5 zeros and 3 ones. You can pick, and the answer is 4. So you can pick this, all of this you can pick. Okay. So let's see what how to write the recursive solution. The constraint are like 600 and each length can be of 100. So we can definitely go for a n cube solution. So a 3D DP would work here, would definitely work here. So what to do? First I will write the recursive solution. Okay, so I will go for the recursive method, and I will, as I used to do, I used to write a calc function in recursive, and I have an index value which is starting from the 0 index, and initially current M and current N I have 0. My bag is completely empty. Okay, my bag is completely empty, so I have 0 of them. Now what I will do is pretty simple, pretty easy also. I will take this vector of strings as input. Okay, vector of string, I will take this as input. I also have the index. Okay, and M and N definitely I will pass it. Definitely I will pass this M and N. Okay, so not the index first. So the constant thing we pass first. Index, and we have current value of M, and also we have current value of N. Okay, so now what you do is that you take the length of the string as the strings dot size, and definitely you go for the base case. Now the base cases will be something like if you reach the last index. So if index is greater than equals to N, okay, it can be equal to also. I can just put it equal. I will just putting it for safety. Then you don't have anything more to loot. Okay, you don't have anything more to loot. You have no possible element to pick up, so you just return 0. Okay, and now what happens if also you do something like current M, current value of M goes to M. Okay, if you have reached your element M, or and so and you need to put current value of N goes to N, then you also return 0. This, what does this mean? This definitely means that both my stacks are completely full. Both my stacks are completely full. You don't need to fill anything else. So you just return 0. It means that these are the base cases which we write. Okay, and quite simply, I will just count in this particular index how many such zeros and ones are there. So in my current index, in my current value, how many zeros exist and how many ones exist. So I will just what I will do is go through all the values of this strs dot index dot size. Okay, so I am going through the size of this, and I am just picking up if the string, I'm going through the string and telling that if this character of the string is a 0, so you increment by 0, or otherwise you just increment by 1. Okay, so you have the count of zeros and ones now. Now if you can put an element or not in the string, that depends on whether on the current m or n. Okay, so take not take, I will just do take not take. So when can I take if my current value of m, okay, my current value of m, if I'm adding zeros, m means zeros, right? Let me check first. Yeah, m means zeros. So if I am adding my zeros to the current value of m, and it is less than or equal to m, okay, and also if my current value of n, the current value of n, I am adding to that 1, all the ones, current one, and I am getting still less than n. Okay, you do understand, right? Yeah, if it says that whether I am able to fill the cells, so it just tells me that whether I am able to fill, whether I am able to put things in both containers without overflowing. Containers without overflowing. So I just want to check that it does not overflow. Okay. If it is possible, then only I have the choice to take it. So I will, if I will take it, if I take it or not take it, whatever. But if I take it, I will have to call my calc function, and one will be the reward because you are asked to return the size of the largest set. The size is given nothing by but the number of elements. So if you are selecting this element, your number of elements gets increased by 1. Okay, you have the strs now. M and n remain same. You go to the next element. Okay, you have already taken this element. Now you go to the next element, go to the next index. Okay, and current value, since you have already taken, the current value get incremented by current value of m get incremented by the number of zeros, and the current value of n get incremented by the number of ones. So that's simple, that's quite easy. If you do not take, you can also have the option of not taking. That this option you have always. There is no if criteria for this option. Even if it's possible to put things in the container, I may take or not take, and if it is not possible, then I will definitely not take it. Okay, so you do understand these things, I think so, because if you do not understand this simple recursion stuff, I will suggest you to go and watch my previous videos, because it's quite simple thing what I'm doing. And you see, I go to the next index, but I did not update my current value of m and n because I did not take this element. And at the end, I will return nothing but return maximum of take and not take. That's all I need to return. If you see, that's all I need to return. Okay. So let me run this and check what is the result, whether I have done some mistake or not. So you see redefinition of n. So I will call this size because n is already there. So I will call this size. Okay. I will call this as size, not the n. Okay, because n is something else. N is the number of ones here. So that is there. So you see, we have the accepted thing. If you try to submit it, you should get a TLE because of the recursion, number of nodes in the recursion. As I've told you many times, it's of order of 2 to the power n. Okay, so definitely you got a TLE here. So in order to not get a TLE, what you will do, you initialize a DP array. So now this will be 3D DP, since the states of the DP are nothing but the index, current m, and current n also. So you can initialize a vector of vectors, that you can do it, but I will not suggest you to do that. What you do in these long DPs is that you can initialize some DP outside it, and you can fill the upper bounds. Okay, so the length, the current value of the length is can go up till 601. So you just initialize it in this way, and 101 because this will be the value of m and n. And as I had told you already earlier, that you need to set the value of the DP to -1. All the elements you need to set it to -1 when you convert from recursion to memoization. Okay, so now I am converting from recursive to memoized or catching solution. Okay, or catching solution. I am just doing it. I am, since this is the recursion tree is exceeding, I will just catch the values. So this is the function memset function of how I initialize it. And you do not need to pass DP or anything in this case. And what you do here is simple, is that if you see the my DP array is empty, DP of index current m current n, okay, all of it is empty. You see, if it is empty, what you can do, you just return the value DP of, if it is not empty, you just return the value. If it is empty, you go further and check. And once you go further, you definitely need to save the state. You definitely need to save the states. What states you will save? So you can just copy this. Okay, so you need to save the state. So you are catching it, you are storing it as a cache memory. Okay, and in the cache memory you are seeing that if its cache memory is filled, then just return it, do not do any computations. And the cache memory, if it is not filled, you just go and save the states. After doing some computation, you just go and save the states. So that's all, that is what you need to do. So if you try to run this problem, if you try to run this code, you will check something amazing. Is that you have the accepted thing, and from TLE, I think from TLE, you will have the accepted case. Okay, and it has also an okayish runtime and memory complexity. So if you try to tell me that how to write directly the function, the iterative function. So I will, as I have already told you, the method of conversion from memoization to, I have already told you the method of conversion from memoization to tabulation. Okay, you already know it, right? And I have done it many times in my previous videos. So this video, I want you to directly write the DP table and directly do stuff. Okay, so how will you do it? How will you do it? Because at the end, gradually, you need to directly write the iterative DP because that will be very much helpful if you can do so. Okay, so you know that you think in exactly the same manner. Okay, you have three states of the DP. Okay, you can have the index. Okay, index can go from size. It can go till the size. So size, you can just store it. Here start size. And you also have m+1 and n+1. Okay, so now as I told you, you need to write the base cases. So the base cases was this index. So if so, what you can do is that you go from index I to this equals to m. Okay, I plus plus, and then again you go to j, and j till m you go. And what you do is that you say that if my index size is already the last element, then I don't have anything to take, and you do DP of size I and j. Okay, so you put it 0. So I am writing the base cases here. I am doing nothing but writing the base cases here. Okay. So if you did not understand what did I do here, this should be understandable. I mean, you should, if you have watched my previous videos, you have already understood how to write the base cases. I am doing nothing but this. I is nothing but my current m. I is nothing but my current m. This I is nothing but my index. Okay. Uh, I in the DPIJK, when I will introduce the DPIJK. Okay, I is nothing but the index, j is nothing but the current m, and k is nothing but the current n. So here I and j are the second two dimensions which I put. And if I am telling that if you reach the last index, after the n value, so if you have crossed the last index, you have nothing to take more into your subset, and you just initialize the DP elements to 0. And you also need to tell them that if for m and n, you also need this. Okay, so for all sizes of the DP, you just go and initialize DP of I and m and n to be zeros. What does this mean? This means that in the m and n, you go to the m and n and tell that if it is filled, if it is already filled. So this thing I am doing nothing but this thing. Okay, if current m is m and current n is also n, then return 0 because your stack is completely full. You don't have anything to take more, so it's completely filled and you don't have to do anything. Okay, now comes the interesting part for dpijk. This is an iterative DB first of all. So you start from the bottom up approach. As the last, these are the last elements if you fill, if you can visualize. So I will just fill this from bottom, and the other two elements also I will fill from the bottom. Okay. So from M, I've already filled the SZ case. So I will go and fill the JM minus 1, J minus minus, and this for integer k equals to n minus 1, k greater than equals to 0. So I am iterating backwards. If you see, I am just iterating backwards. But what you do is here, you just take a string s and extract the ith string. So this is nothing but I stands for index and j stands for nothing but current m. Okay, k stands for nothing but current n. Extract the index strs of I. Okay, extract the index and you iterate through this. So you take some different variable, let's say x, and you iterate through this s. Let it be c, character c. Okay, since this is a character, I will take it to be a character c. So now what I can do is very simple, very easy. I will just uh, store my count of zeros and ones. So I have my count of zeros and ones as initialized to zeros, and if I see if c is equals to this one, I will just increment this one, and else I will increment this 0. So I have the count of zeros and ones at every index ready. Okay, I have that every index at ready. Now I need to check if it is possible. I will take or not take. So if I can take, so it means that if j plus this 0, okay, this is m, this is less than or equal to m, and uh, k current n plus 1 is less than or equal to n. So I am doing nothing but the exact same thing as I have done here. If you can see, the current m is nothing but the j here, current n is nothing but the k here. So I'm just replacing there only j and k. If you can take, so if you can take this, what you do, if you can take this, you just have the dpijk that you can either take or not take. So maximum amount take or not take. Okay, maximum amount take or not take. But what is this take? What is this take? You can take, if you are taking, then do dpi. You go to dpi plus 1 from I, and j value you increment to 0, and k value also you increment to 1. Okay, and not take, if you are not taking, what you will do, you will just go to the next element without updating the j and k. Okay, this is the thing which you need to do. And else if you don't have, if you cannot put, the only thing you can do is not take it. Only thing you can do is not take it. So you only have one choice now, not take it and move forward, because the thing which you have now, if you put it in the stack, it will exceed the amount. It will exceed the amount. So this is what I am telling, that you should be able to write this directly without doing the recursion and memoization. So gradually you need to do this. Okay, there's no hurry. As I already told you, in online test you can write the memoized solution. There is no hurry for that. To be safe, you can draw it, but definitely if you are looking for improvement and doing better and better, definitely you need to able to write this iterative solution from the at the first in the beginning only. So you return nothing but dp000, because you know that dpijk denotes nothing but starting from the index I and having the ith, having the j and k values at current as current m and current n. What is the maximum thing I can? What is the maximum subset I can take it? So this tells me nothing but starting from the index 0, start from index 0 and empty sacks, both the sacks empty. How will you, what is the maximum element, what is the maximum subset that you can fill? So I think that this is all and this should work. Let me try to see if it works or is there any error that I committed. So it shows that we do have a wrong answer. So let's see what can be the possible error here. So if you see, this j should not be starting from m-1 or n-1. It should have m and n. Why? Because I am starting from size -1. That is because for all other values, for both the other indices, I have initialized the size as 0. So the size has no choice but to start from 1. But m and n do have some choices. I mean, when m can be 0, n can be full also, right? Here I am considering the AND case only. AND case means both m and n are 0. So if m is 0, I mean, if m is full, n can be some less also, right? So that thing you need to take care of. The j and k, you just need to initialize that by m and n. And now if you try to run and check, you will have the accepted thing. And if you submit it now, if you try to submit and check, yeah, you do have an improved runtime complexity as well as memory complexity as you as you have gotten rid of the stack memory in the recursive DP. Okay, so that's all for this video, I guess. I will meet you in the next video with grid DP. So some variations of knapsack I have done. So total as of now I have done the 1D DP portions. Okay, 1D DP is done. I have done knapsack. I have done the 0-1 knapsack problem from GFG, and I have done some variations of knapsack, which include some coin change problem, two coin change problem from Leetcode. I have done. Okay, coin change two problems are there, and this 3D DP variation also I just showed you. I will do more variations when I will do DP with algorithms where, let's say, binary search and stuff like that all will also be involved along with DP. So I will also show you those, but let's move it slowly. Okay, in the next video I will be starting with DP on grids. Okay, so how the approaches should work there, I will completely explain with the help of some problems of Leetcode. So yeah, that's all for this video. I will meet you in the next video. Definitely keep following my playlist. Thank you so much. Thank you.